Now let's take a look at example 7. Let's suppose, again, much like in our opening motivation, we have a particle that's moving in a straight line. But instead of understanding the particle's velocity at any given time, let's suppose that we're given its acceleration. And its acceleration is given by a of t is 3t to the third plus 3 cosine t. And I know that the velocity of the particle at time 0 is 7 meters per second, and the position at time 0 is 10 meters to the right of the origin. So if my particle is moving here on this number line, I know that its start location is over here at the value of 10. So I'm going to try to attempt to find the position function of the particle. So again, it might be helpful to remember that there is this connection between our functions and our function of the position and the functions of velocity and acceleration. Specifically, if I take derivatives, I move down this chain. And so if I want to find s of t, I can do antiderivatives to climb back up the chain. So if I'm starting with a of t, I'm actually going to need to do 2 antiderivatives to get all the way back to the value of s. So let's go ahead and actually try to start this. I'll go ahead and see that if a of t is equal to 3t to the third plus 3 cosines of t, then I could start by attempting to find v of t, climbing back up one step with an antiderivative. Notice here, my power would have to go up to 4, and then I would need to have 3 over 4 here, so when that 4 comes down, I can cancel the 4 in the bottom, and I'm right back to where I started. I can also see here that I'm going to get plus 3 times the sine of t. So again, when I take the derivative of this, I go to 3 cosine t. And I'm going to have a value of c. Now, before I do an antiderivative of this, it might be helpful to see if I can figure out what this final value is for that constant. So I'll note the following. We are told that at time 0, my velocity is actually 7. And so, if I was to go ahead and try to work with this, that would mean that I should get an answer of 7 whenever I plug in my value here of 0. So let's see what we come up with. What would this give me for the value of c? Well, obviously this first part here is going to be 0. Sine of 0 is going to be 0. So actually here I'm just going to be left with 7 is equal to c. And so thus, we could actually write our v of t as 3/4 t to the 4th plus 3 sine of t plus 7. So this is great. Now that we have v of t, I can imagine climbing back up one more time. So now I could state that s of t is going to be equal to, let's see, this would have to be t to the 5th power now. So I'm going to have to divide by an extra 5, and that would give me 3 over 20. Again, you can just double check your work here by taking the derivative. Over here, I'm going to get minus 3 cosine of t. I have to go to a minus because remember when I take the derivative of cosine, I'm going to get negative sine. And so I need that negative to combine with this subtraction and turn me back to plus. The antiderivative of 7 would be 7t. And then I'm going to have to add on a constant here. Now to avoid confusion, I'm going to go ahead and maybe give this a different letter name. Or maybe I could call it, like I could change this to c number 1 and have this be c number 2. For the moment, I'll just use the value d. Again, the reason I do that is that I don't want to accidentally think that, oh, that should also have the value of 7. This is a different number and might have a different value. Now again here, I should be able to find what this value is by recognizing that we are told that at time 0, I get the value of 10 for my position. And so, it must be the case that 10 is what I get when I plug 0 in here. And so let's see what we end up with when we do this. So I have cosine of 0 plus 7 times 0 plus d. So obviously this 0 to the 5th power, that term's going to be 0. 7 times 0 is 0. And I'm going to be left here with 10 is equal to, let's see, cosine of 0 is actually 1. So this is going to be negative 3 plus d. And so I'm going to get d should be the value of 13. And thus, I can end with that s of t should be equal to 3 over 20 t to the fifth minus a 3 times the cosine of t plus a 7t, and finally plus the value of 13. So what I can see here is, again, I was given an initial value problem, but that I actually was required to kind of take multiple antiderivatives. And that's totally possible. I just have to take one antiderivative and then another. Much like in the same way if you had to take a second derivative, you would just go down this list twice. And sometimes I might be required to climb this list multiple times over. So this ultimately completes section 4.10. And at this point, it's important to note that it's easy to get the wrong impression about antiderivatives. So in general, finding antiderivatives of a function can actually be really, really difficult, or maybe even impossible in certain instances. So on the other hand, differentiation can always be applied in a standard way to the functions in calculus. So while moving down this list is very, very simple, moving up this list is extremely challenging in certain instances. So to get just a general idea of what I mean, you can take a look here at some very, very difficult functions to find antiderivatives of. What if I told you that f of x was a function of the natural log of x, and I wanted to know where did it come from? That's really difficult. What if I said g of x is equal to the inverse sine, or sorry, g prime of x is the inverse sine, and I wanted you to find regular g of x. Could we do that? What would I take the derivative of so the answer is inverse sine? What if I said something like h prime of x is e to the negative x squared? What in the world would I take the derivative of to generate this? Again, going down the list, finding the derivatives of any of these functions, very easy. But sometimes finding the antiderivatives are very difficult because, as you might note here, we have no derivative rules that we've memorized to understand how to work with these functions in the reverse order, nor is there any easy algebraic moves we can make to rewrite these things. So keep in mind that when you're working through some of the examples in this section, that a lot of times we're gaining or we're able to work with very, very easy sorts of functions to kind of reverse the order of. And these functions and their antiderivatives will become important later in Calculus 1 as well as within Calculus 2. So keep this in mind and appreciate actually the simplicity of some of the questions that you're coming across. But if you're really looking for a challenge, I dare you to try to actually find yourself antiderivatives of these guys. They're very, very difficult, and it leaves a little bit of mystery to the process of how difficult is it to climb up this ladder for certain chains of functions.